Okay, it's Brian, and we're going to talk about using energy. And this is the stuff of basically chapter 11. So I want you to have read the relevant sections of chapter 11. But here's the question. When you're doing some sort of a task, we want to know how much energy does your body actually use to complete that task. And that is a question of efficiency. And here is someone measuring the efficiency of an elephant for locomotion, and actually they're ridiculously efficient, and that's something we'll talk about later. But for starters, I want to do another installment of things I like about your generation. And when I talk with people your age, I'm really struck by the sense that in everything that you try to do, you really try to do the right thing. You think carefully about your actions and how they affect other people. And you do this more than any generation of students I've worked with previously. And so I very much appreciate that about you. You look at a situation and you ask yourself, what's the right thing to do? And then you do it. Thank you for that. Now, here's something I want to mention. I'm frequently going to talk about energy being lost. But when I talk about energy being lost, I'm really talking about it being lost in quotes, because energy is never lost. It can be lost to our use, and this is a point we'll keep coming back to, and that's what I mean. It gets converted into a form of energy which is not useful, about which more later. Now let's talk about efficiency. Okay, if I have a 100-watt incandescent light bulb, it only emits about 4 watts of visible light, and that is true. That's why incandescent light bulbs are terrible. The efficiency, what is that? Well, you know it's about 4% efficient, because we define efficiency this way. It is what you get divided by what you had to pay. In this case, what you get is light. That's why you have a light bulb. You get 4 watts. What you had to pay was 100 watts of electricity. So my efficiency is about 4%, which is terrible. Compact fluorescent bulbs are better, okay? To get 4 watts of visible light requires only 25 watts of electricity input, and so the efficiency is better. It's more like 16%. But you can do even better if you have LED bulbs. Now let's talk about the concept of efficiency in terms of how your body works. So first off, let's consider a case where you have someone carrying a load on level ground at a constant speed. Okay, in that case, you're not doing any work. Okay, you're not raising anything up. You're not pushing anything. Your kinetic energy is not changing. Your potential energy is not changing. What you get in an energy sense is nothing. It is nothing. So in cases like that, if we're going to define the energy that your body uses, we're going to look it up in a table. But I have a second case, which is this. If you're climbing up a set of stairs, what you get is a change in potential energy. And in that case, I can compute some sort of efficiency because I have something that you get. I have an energy output that I get. And then I can divide that by what you had to pay to do that to calculate an efficiency. So we will have 2 different types of problems when we're looking at energy in the body. First off, if I have problems of type 1, you're just walking on level ground, you're riding a bicycle, you're sitting and doing your physics homework. In an energetic sense, you're not doing anything. And so we just look up energy use in a table and say, how much energy does your body to use when you're doing this particular thing? But I have problems of type 2, like climbing stairs, where I'll compute the energy use by saying, I'm going to figure out what you get, which is a change in potential energy as you raise your mass, and then I can compute the energy use by using the efficiency of your body. And we're going to assume that your body has a 25% efficiency. Now, it turns out that's not exactly true. It varies depending upon the kind of task that you're doing, but that's a pretty decent estimate. Okay, so I can compute the energy used by your body is 4 times the energy actually needed to complete a task. Okay, that's how we're going to compute the energy that your body uses to complete a task. Now, let's relate this back to our basic equation. Here's our basic equation for energies. Now I've added chemical energy to the picture. If you're walking on level ground, you're just turning chemical energy into thermal energy. Okay, you're not getting any useful form of energy because thermal energy isn't useful for doing work, as we'll talk about later. When you walk upstairs, you're increasing your potential energy and you're also generating thermal energy. So we can compute what you get, which is your change in potential energy. What you paid is the chemical energy your body had to use to make that happen. Now, when you do when your body does things, you get your energy from food, okay? And the calories on the side of a food container are the energy input. And one big C calorie is equal to 1,000 little c calories, as you probably know. And 1,000 calories, little c calories, is equal to 4,200 joules, or 4.2 kilojoules. And joules is the preferred form of energy that we like to use. So if you have food that has calories in it, and you're given the calorie content of it, you can convert that to joules like so. Or if you compute some sort of a energy in joules and you need to convert it to how many calories of food does it take to complete a task, we use that conversion. So here's a question. Suppose you had a 75 kilogram person climbing to the top of the Cape Hatteras Lighthouse, which is a total climb of 59 meters. How many Little Juan bean and cheese burritos would this task require? And those are the little tiny burritos that I used to get in the freezer case at the Safeway. And each one of them had 240 big C calories, which is equal to 1,000 kilojoules. And that's why it's a very useful unit of energy. So let's think about how we'll solve this problem. First, we're going to strategize. Now this is energy in the body problem type number 2, because we clearly get something. What we get when we climb up the lighthouse is I get a change in potential energy. Okay, so I can compute what I get, and then I can multiply by a factor of 4 to get what I had to pay. And to prepare, what I'm going to do is I'm just going to draw a before and after visual overview, as I always do. So a person starts out here, not moving. Person finishes at the top of the lighthouse, again, not moving. They start out on the ground, so at a height y is equal to 0. They finish at the top of the lighthouse at a height of y is equal to 59 meters, okay? And the energy that has changed is the potential energy. The person changes their potential energy, and the amount that the potential energy changes by is just equal to m times g times the change in height. Okay? Next, we can solve. Okay, the energy that the person gets was a change in potential energy, which was m times g times y. Well, the mass is 75 kilograms. G is 9.8 meters per second squared. Y, the change in height, is 59 meters. And so if I compute the change in potential energy, what I get is 43.3 kilojoules is what I get. But the question didn't ask that. It didn't ask what was the change in potential energy. It asked how many bean and cheese burritos does the task require. So then what we do is we say this. This is what we get. The question is asking, what did we actually have to pay? And what we paid to do this is going to be equal to 4 times the change in potential energy. And so if I compute that and I round that to two significant figures, I get that's 170 kilojoules. So it takes me 170 kilojoules to walk to the top of the lighthouse. And that seems like a lot, but a Little Juan bean and cheese burrito has an energy content of 1,000 kilojoules. So it takes approximately 1/6 of a little tiny burrito, and that is a little tiny burrito. So really tiny ones, I used to eat 2 or 3 for lunch, depending on how hungry I was. Okay, that is not a lot of food, and 1/6 of those is sufficient to power your climb. And my assessment for this is, wow, your body is relentlessly efficient, and it is. It takes just 1/6 of this little tiny burrito to get you all the way to the top of the lighthouse. That is kind of crazy, but is in fact right. Your body is very, very efficient in performing tasks. And you can compare this number to other numbers that you're going to calculate. Now here's another question. Your body used 170 kilojoules of energy. Okay? That was the energy from the bean and cheese burritos. You only got 43 kilojoules of change in potential energy. So that was your chemical energy that you used. Potential energy was only 43 kilojoules. What happened to the missing 127 kilojoules? And what happens is that turns into thermal energy. The lost energy ends up as thermal energy. You just exhaust heat into the environment. Now I want to talk briefly about this. Your body uses energy even at rest, and actually over the course of the day, that's mostly what you use. And there's a table of values in the textbook, and I just want to point something out which is kind of amazing. Like, you would think, I want my brain to be the #1 energy user, or maybe my heart, but it is not. It is your liver. The liver is the underappreciated organ in your body. It's using 1/4 of your metabolic power at rest, which is kind of crazy, actually. But it's doing a lot of hard work. It's doing a lot of chemical work, and that's hard stuff. Now, we saw on the previous slide that your brain uses about 20% of your body's metabolic power. It only makes up about 2% of your body's mass, but it's using 20% of your body's metabolic power. We have really expensive brains, and clearly they're doing important things because they're worth that level of energy expenditure. But I think about this fish. This species of fish right here, its brain is 3% of its body mass, bigger than yours, and it uses up to 60% of its metabolic power. So this is a very, very brainy fish. And there must be something amazing that this fish is doing with all of that energy, because this is, it's using more than half of its energy to run its nervous system. So clearly it's getting something very valuable from this, and it is. And we're going to talk about what it is in the second semester. This is a question for Physics 122. Now I want to do another energy problem, okay? And here's the question. Jessie bicycles at 15 kilometers per hour for 1 hour. 2 questions. A, what is the metabolic power? B, how much energy does her body use during the ride? My strategize step is just to say this. This is energy in the body problem type #1, because she's riding at a constant speed on level ground. And we're not told that, but let's just assume that that's true. So she's cycling on level ground. She's not changing her kinetic energy, not changing her potential energy. How do we get the energy? We just look it up in the table. And the table values that you're given in the textbook are for a 68 kilogram individual. And conveniently, Jessie has a mass of 68 kilograms. So, and this was supposed to say prepare. I forgot to edit that. Oh, heavens to Betsy. So my prepare step is to say, I'm just going to look up the number in the table. And the amount of energy that she's using is 480 watts, or 480 joules per second. And that is her metabolic power. That is what her body is actually using. And then, how much energy does her body use during the ride? Well, I can just compute that by noting that the power is equal to the change in energy divided by the time interval. And so her body is using energy at a certain rate. And if I know the rate, which I do, and I know the time interval, which I do, I can calculate how much energy is used. And this says prepare. Oh, heavens to Betsy. I probably just stuck in an extra slide. Let's forget that happened. So let's forget this slide exists. And move on to the solve step. And my solve step, I'm just going to compute. And we said that the power was equal to delta E over delta T. And I was looking for delta E. Delta E is just equal to the power times the time interval. Well, the power that she's using energy at is a rate of 480 joules per second. And she does that for 1 hour. 1 hour is 3,600 seconds. And so I compute the final energy. And I get an energy of 1,700 kilojoules. And that's like 1.7 Little Juan burritos to power the ride. And my assessment is this seems about right in terms of other numbers that I've seen for the energy, the rate at which your body uses energy and how much you use to perform certain tasks. And as you do more problems, you will get a sense of that scale. But I want to look at a third thing, and this is kind of remarkable. So suppose Jessie is doing this bicycling. We're going to power the forward motion with an electric motor. What power output motor would be required? So we're going to replace Jessie with the motor. What power output motor do I need? I want to think about this. Your body is only 25% efficient. So what that means is, of the 480 watts that your body is using, okay, only 25% is going to forward propulsion. So the amount of energy that's actually going to forward propulsion is 120 watts. 360 watts are going to thermal energy. So the power to make Jessie go forward, 120 watts, 120 joules per second. She just needs a 120 watt motor, which is not very much power at all. That is less than any of my kitchen appliances, which is kind of remarkable. And I think the surprising fact to me is it takes so little to make you go forward. Bicycling is a really, really low energy sport. If you look at an elite racing cyclist at the peak of their form, going at it hammer and tongs, their output power is about 400 watts. It's about 400 watts. That's about the same as a big television set would use. I say it's less than any of my kitchen appliances. It's less than my blender, less than my microwave, less than my mixer. Anything. I don't have anything in the kitchen which uses that little power. It's not very much at all. It's kind of amazing. And to put it in perspective, this mobility scooter here has a power of about 400 watts. And so what cyclists have done is they've just made bicycles that use very, very little energy to go forward. And so what's the least energy you can use going from point A to point B is by getting on a bicycle and riding your bicycle, which is kind of a remarkable thing. Now, we've been talking about energy use in the body, but now we want to talk about energy use in things called heat engines and heat pumps. And that is another big topic in Chapter 11 that we'll take a look at. And we'll do that in the next set of annotated slides.